Hello and welcome to the video presentation of our K&E 357 PLC based automated greenhouse project. To test our concepts, a small model prototype of a greenhouse was made. Heat energy to simulate the sun's rays was introduced to the system via a 50 watt 12 volt DC halogen lamp. This required 4.17 amps to run it at 12 volts, and the current limited benchtop supply was only able to provide 6.8 volts.
The 12 volt DC fan at full voltage draw requires 0.12 amps, and the digital input output relay module provides 24 volts. A series resistor with the fan to limit the voltage seen by the fan as 12 volts, which we calculated knowing that at 12 volts there will be a current draw of 0.12 amps approximately. We can then work out that a 100 ohm resistor is necessary for the fan to see 12 volts. Here is that circuit in real life with our positive input coming from the relay module, which on our circuit diagram is this point here, this node here. This is our power supply, which is as seen internally on the relay module. That will be supplying 24 volts to this side, and there is our internal relay. We needed to place a 100 ohm resistor in series with the DC fan for 12 volts to be seen across it, 12 volts to be seen across it. Inside the environment we have a thermocouple, which is run directly into the analog module. This is a thermocouple K, and there is another thermocouple here providing a control reading to compare with what has been scaled for the input of the program.
Originally it was considered that a PID loop would be the best option. This is the operator screen of a PID simulation made in Unity Pro. All the variables can be altered, and the overlaid graphs give us live feedback on how the system will react to these changes.
Our simple latching function block diagram in Unity Pro. This is currently loaded and open, so and it's sunk to these two positions on this relay module. As you might have heard, as I switch that on, we do receive our necessary 12 volts there to provide voltage to the fan, and our latching circuit is also functioning as intended. Now if we use our off button, we see that it goes off, and also that our latching circuit is now being deactivated. On, off, and we can also force that in Unity Pro, either by creating an animation table, and we can force start to on, which as you can see forces our display light on and our fan on. Now let's force that back off, and we can force our stop function, and we'll force that back to 0. Quit out of that. Or if we wanted to, we can force the function from here. Now the program is currently running. We have a set point for 24 degrees. The thermocouple input receives a value between minus 231 and 1331. This has then been scaled to a temperature in Celsius, which is currently reading 19 degrees. This temperature value is then compared to our set point of 24 degrees. If it is less than, the latching circuit will turn the fan off, and if it is greater than or equal to, the fan will be switched on, and the fan in this latching circuit will retain the fan in the on state. Alright, now we can see that there is a slight difference in our temperature readings. This is due to calibration of the thermocouple case. Let's switch the sun on and watch our temperature increase. It's increasing quite rapidly over there and also within our program. Now, you should see once this reaches 24 degrees, you'll see the fan on. Will be activated and switch the fan into the on state. And there we have it. And it reacts, the system reacts very rapidly, causing the fan to switch off very quickly. There's also a display light to show the status of the fan. Red is on, and off is off. Now, since the control volume here was so small, comparative to our fan, I've created an imitation mover here to let the air flow through, and so there's not a reverse differential sucking air back through the fan when it's meant to be projecting outwards. Because our air holes were not sufficient for the amount of air being moved. Alright, so we can see that our temperature control is being moderated at 24 degrees quite nicely. And in an autonomous fashion, there we have it. 24 degrees greenhouse. And I'm just measuring the voltage across the fan on the right there. Excellent. See if we switch the light off, the system will cool. Now I did want to have this halogen globe running from another relay module, input and output, to be controlled in a sense that you could increase the temperature and turn it off. But the current draw, this is a 50 watt halogen globe with a 12 volt input, required far more current than I had any resistors to build a bucker circuit to control that. So we're manually switching the sun simulation on and off at the power supply. Like so. Look at our analog inputs and then our relay module. And that's the first output. Switching on. Fantastic. 24 degrees. Lovely.